Ever imagine like holding something the size of a grapefruit,
Oh.
but it has like the power to wipe out a whole city?
Yeah.
That's what we're diving into today.
Wow.
It's called a demon core,
Okay.
a plutonium core
Uh-huh.
from World War II that was involved in not one, but two fatal accidents.
It's really a story that captures the just raw power of nuclear energy, I think,
Right.
and the sobering consequences of miscalculation
Yeah,
in those early days of research.
for sure. And I think we're talking about the Manhattan Project era, right?
Exactly.
A time of incredible scientific breakthroughs,
Yeah.
but also just tremendous risk.
Yeah. The world had just witnessed the destructive force of atomic bombs,
Right.
and there was this urgent push to understand and control this new form of energy.
Yeah,
But as with any pioneering science, the dangers were still being discovered.
of course.
Yeah,
And the demon core became a tragic symbol of those dangers.
absolutely.
So I'm curious what made this particular core so dangerous. It wasn't like constantly on the verge of exploding, was it?
Not in the conventional sense.
No.
The danger lay in its potential to go critical.
Okay.
Think of it like a room full of mouse traps,
Okay.
each set with the ping pong ball.
Okay.
If you toss one ball in,
Yeah.
it triggers a chain reaction with balls flying everywhere.
Okay.
That's essentially what happens in a nuclear chain reaction.
Got it.
Except instead of ping pong balls, we're talking about neutrons splitting atoms and releasing tremendous energy.
So the size and the shape of the core matter because
Yeah.
they influence how easily that chain reaction can get going.
Precisely.
Yeah.
The demon core, a 6.2 kilogram sphere of plutonium and gallium,
Wow.
was only 95% of what's called a critical mass
Okay.
under normal conditions.
Okay.
It was essentially a hair trigger,
Wow.
incredibly sensitive to any changes that might reflect more neutrons back into it and set off that chain reaction.
And those changes sadly came in the form of two accidents.
Yes.
So tell me about the first one with Harry Dahlian Jr.
So it's August 21st, 1945.
Okay.
It's late, and Daglian, a young graduate student, is
Right.
alone in the lab.
Well, they let him work alone with
Yeah.
something that volatile.
Again, these were the early days, and safety protocols were still being developed.
Right.
The danger wasn't as fully understood as
Right.
Daglian carefully positions the bricks.
Yeah.
He's essentially pushing the core closer and closer to criticality,
Uh-huh.
and then a slip of the hand,
Oh,
one brick falls onto the core.
oh, wow.
There's a flash of blue light.
Yeah.
That's Cherenkov radiation,
Right.
a visual marker of the immense energy being released.
Right.
Daglian reacts instantly, knocking the brick away,
Okay.
but he's been hit with a massive dose of radiation.
Wow.
He dies 25 days later from acute radiation sickness.
It's almost hard to fathom that a moment of clumsiness leading to such a devastating outcome.
And it wasn't just Daglian.
Right.
Even the security guard who was present, though, further away later, died of leukemia,
Oh, wow.
potentially linked to that exposure. This really highlighted the invisible, lingering nature of radiation's effects.
Yeah. So after this horrific accident, surely they overhauled their safety procedures.
They did implement changes.
Okay.
They restricted who could conduct experiments,
Uh-huh.
mandated multiple monitoring devices,
Okay.
and required at least 2 people present during these types of tests.
Right.
There were even discussions about conducting them remotely to minimize risk,
Yeah.
but as we'll see, it wasn't enough to prevent another tragedy.
Which brings us to the second accident with Louis Slotin.
Yes.
Wasn't he involved in investigating the first accident?
Yes, he co-authored the report on Daglian's death.
Wow.
This is May 21st, 1946.
Okay.
Less than a year later,
Wow.
Slotin, a senior scientist,
Yeah.
is conducting an experiment using a beryllium sphere to reflect neutrons back at the core.
Okay.
But instead of using the design spacers to keep the sphere halves apart,
Right.
he's using a screwdriver to control the gap.
A screwdriver. That seems incredibly risky.
It's hard to believe now, but that's what happened.
Wow.
The screwdriver slips, the sphere halves close, and the core goes critical.
Oh my gosh.
There's another blue flash.
Yeah.
And Slotin, realizing the gravity of what's just happened, utters, "Well, that does it."
He knew in that instant what he'd done.
Yes, he did.
Oh gosh.
But even in the face of his own impending death, Slotin acts heroically.
Wow.
He immediately kicks the sphere apart, stopping the chain reaction.
Wow.
Then, despite suffering from a lethal dose of radiation himself,
Yeah.
he starts documenting the positions of everyone else in the room to estimate their exposure.
That's incredible. A selfless act in the midst of such a dire situation.
He died 9 days later, but his quick thinking and actions likely saved the lives of the other scientists present.
Wow.
Though some did suffer long-term health consequences.
These two accidents are incredibly tragic.
Yes.
And I'm struck by how they both involved seemingly small slips or miscalculations that led to such devastating outcomes.
It underscores the immense power they were dealing with, and how even the slightest error could have catastrophic consequences.
Right.
But the story of the Demon Core doesn't end there.
Okay.
These were just two of many criticality accidents that occurred during this era of rapid nuclear development.
There were more.
Yes.
I'm eager to hear about those and how the lessons from these tragedies shaped the field. Let's delve into that in part 2 of our deep dive.
Yes, sounds good. So as we kind of dig deeper into these other criticality accidents, it becomes clear that while human error was often a factor, there's a bigger story here.
Okay, what do you mean?
It's easy to focus on the individual mistakes, right?
Right.
A slipped screwdriver, a dropped brick.
Yeah.
But these accidents often reveal deeper systemic issues within the facilities themselves, things that made these tragedies almost inevitable.
Like what kinds of issues?
Well,
Like, give me an example.
Let's go back to the Mayak facility in Russia, 1953.
Okay.
Remember, the workers transferring plutonium solutions didn't even realize they'd triggered a criticality event? Right.
Because they lacked the training to recognize the signs?
Right.
But it wasn't just about their knowledge.
You're saying the facility itself was a problem.
Exactly.
Yeah.
Investigations revealed that Mayak was operating well beyond its safety limits.
Wow.
Plutonium containers were arranged in a way that increased the risk of a chain reaction.
Okay.
And they were holding far more material than they were designed to handle.
So it was a recipe for disaster waiting to happen.
Right.
Not just one person's fault, but a system set up for failure.
That's a key insight that emerged from analyzing these accidents.
Yeah.
And we see a similar pattern in other cases.
Okay.
Take the 1958 incident at Los Alamos, where Cecil Kelly, a very experienced scientist, received a lethal dose of radiation.
Wow.
Turns out the plutonium concentration in the tank he was working with was hundreds of times higher than it should have been.
Oh my God.
A breakdown in procedures, a lack of oversight.
Yeah.
These systemic failures played a huge role. It's almost like there was this sense of invincibility in those early days of nuclear research.
Yeah.
Like the scientists were pioneers, pushing boundaries, maybe feeling a bit too confident.
It's fascinating to consider that psychological aspect, right? This was a new frontier of science.
Yeah.
The allure of unlocking the atom's secrets.
Yeah.
The pressure to win the Cold War arms race was immense.
Of course.
It's easy to see how caution might have been overshadowed by ambition.
But as we've seen, the consequences were all too real.
Yes.
And it wasn't just about the immediate impact of the accidents.
Right.
We have to talk about the long-term suffering. Human cost.
Absolutely. These stories highlight not just the acute effects of radiation exposure, but the chronic health problems.
Right.
The psychological trauma that lingered for years.
Right.
Alvin Graves, one of Sletin's colleagues, was the closest to him when the Demon Core went critical that second time.
He was the one who actually flipped the top half of the sphere off, wasn't it?
Yes, incredibly quick reflexes.
He survived, but his injuries were severe.
Oh, God.
He developed cataracts, thyroid issues, and even his death from a heart attack years later might have been linked to that exposure.
Oh, wow.
It's a sobering reminder that surviving a criticality accident didn't mean escaping unscathed.
And the mental toll must have been immense.
Right?
To witness such a sudden, violent event, knowing you were exposed to something so dangerous.
Right.
It's hard to even imagine.
Yeah, you're right. Imagine the survivor's guilt.
Right.
The fear of the unknown, the constant worry about long-term health effects.
Yeah.
One survivor of another accident described it as a living death.
Wow.
Always waiting for the other shoe to drop.
Right.
These were burdens many carried for the rest of their lives.
It's a stark reminder that these weren't just scientific mishaps.
Yeah.
They were deeply personal tragedies that affected real people in profound ways.
And their stories highlight the urgent need to learn from these mistakes.
Right.
To shift from a reactive approach to a proactive one.
So let's talk about how those systemic issues were addressed.
Okay.
How the industry evolved.
Okay, because it sounds like a pretty drastic change was needed.
It was. As the understanding of the risks grew,
Yeah.
there was a concerted effort to improve safety at every level.
Okay.
Facility designs were reevaluated to minimize the potential for criticality.
Right.
Stricter limits were placed on the amount and configuration of nuclear materials.
So taking a more cautious approach, building in safeguards from the ground up.
Exactly. And technology played a role.
Okay.
Criticality alarms were installed, automatic shutdown systems were implemented
Right.
to detect and mitigate potential accidents before they could escalate.
It seems like a shift from simply reacting to accidents to actively preventing them.
Precisely. And alongside the technology,
Yeah.
a new emphasis on training emerged.
Okay.
Workers at all levels, from technicians to scientists,
Right.
were rigorously educated not just on the procedures, but also on the fundamental science behind criticality.
So they weren't just following steps blindly.
Right.
They understood the why behind the what, which hopefully made them more aware of the risks.
That was the goal, to create a culture of safety.
Okay.
Where everyone understood the immense power they were dealing with.
Right.
And took personal responsibility for mitigating the risks.
Yeah.
And this shift in mindset, coupled with the technological advancements and stricter regulations, did lead to a significant decline in criticality accidents.
It sounds like a hard-won lesson paid for with the lives and suffering of those early pioneers.
Unfortunately, yes.
Yeah.
But their sacrifices did pave the way for a safer nuclear industry.
Right.
But we can't forget that accidents can still happen.
Right.
Complacency is dangerous, especially when dealing with such powerful forces.
So even with all these improvements, are criticality accidents still a concern today?
They are, while far less frequent.
Okay.
The potential remains.
Okay.
As technology advances.
Right.
New applications for nuclear materials emerge.
Right.
And with them, new challenges.
Right.
The 1999 Tokamura accident in Japan is a prime example.
Okay.
It occurred in a state-of-the-art facility.
Yeah.
Yet a series of seemingly minor errors, driven by a desire to speed up the process, led to a prolonged criticality event that lasted for 20 hours.
20 hours. That's terrifying.
Yes.
It sounds like no matter how advanced our systems become, the human element will always be a factor.
That's the key takeaway. We can't engineer away human fallibility.
Right.
As long as people are involved.
Yeah.
There's potential for error, oversight, a lapse in judgment.
Right.
Which brings us to a crucial question.
Okay.
What can we learn from the past to ensure the safety of those working at the forefront of nuclear technology today and in the future?
It's a question with very high stakes.
Yes.
I'm ready to dive into that in the final part of our deep dive.
Yeah, it really is a lot to process. You know,
Yeah.
the accidents, the sheer power we're talking about. It feels like we're entering kind of a more philosophical realm now.
Like, what does it all mean?
I think it forces us to confront some uncomfortable truths about scientific progress, that it sometimes comes at a cost.
Yeah.
And those costs are often borne by individuals, by real people whose lives are forever changed.
Of course, it's easy to get caught up in the excitement of discovery, the potential benefits.
Right.
But the story of the Demon Core and all these other accidents, you know, it's a stark reminder of the responsibility that comes with wielding such powerful forces.
Absolutely. And it raises ethical questions that we as a society need to grapple with.
Yeah, what are those?
Well, if the pursuit of scientific advancement inherently involves risks, where do we draw the line?
Yeah, where is that line?
How do we balance the potential for progress with the safety and well-being of the people involved?
It's a tough one because it feels like progress often does require taking risks, pushing boundaries.
Right.
But how much risk is acceptable, especially when we're talking about something as potentially devastating as nuclear technology?
Yeah, that's the heart of the matter.
Yeah.
And I don't think there's a simple answer. It requires careful weighing of potential benefits against potential harms.
Right.
A commitment to minimizing those harms through every possible means.
So it's not just about having the best technology, the safest facilities, the most rigorous procedures.
It's about creating a culture, a mindset, where safety is truly paramount.
Okay, so how do we make that happen?
Well, a culture where questioning assumptions and speaking up about concerns is encouraged, not punished.
Right.
Where learning from past mistakes is deeply ingrained. Where there's constant vigilance, a recognition that complacency is the enemy of safety.
And that feels especially important when you consider the long-term implications.
Absolutely.
These accidents didn't just affect the individuals involved,
Right.
but they had ripple effects on families, communities,
Of course.
even future generations who might be dealing with the environmental consequences.
It's a legacy that we can't ignore.
Right.
And it speaks to a broader responsibility, not just to the people working directly with these technologies,
Right.
but to the wider world, to the future.
Okay, so where do we go from here? How do we ensure that nuclear science remains a force for good, for progress,
Right.
while minimizing the risk of repeating the mistakes of the past?
Well, I think it starts with humility,
Okay.
acknowledging that we're dealing with forces we don't fully understand that can easily overwhelm us if we're not careful. We need to move away from that move fast and break things mentality that sometimes permeates scientific endeavors.
Especially when the things we're breaking could have such catastrophic consequences.
Precisely, we need a more cautious, deliberate approach.
Yeah.
One that prioritizes safety at every level, from the design of facilities and equipment to the training and oversight of personnel.
Right.
And it's not just about top-down regulations. It's about empowering individuals to be active participants in safety culture.
So giving them the knowledge, the tools, and the confidence to speak up if they see something that's not right.
Exactly, fostering a sense of shared responsibility,
Yeah.
a collective understanding that safety is everyone's job.
Right.
And it's about constantly learning, adapting, and evolving our approach as technology advances and new challenges emerge.
It's a tall order, but it feels essential.
I agree.
The stakes are too high to settle for anything less.
The stories of the Demon Core and other criticality accidents serve as powerful reminders of that.
Yeah.
They force us to confront the human cost of scientific progress and to ask ourselves some hard questions about how we move forward responsibly and ethically.
You've given us a lot to think about.
It's been my pleasure.
It's been a fascinating and, frankly, unsettling journey into the history of nuclear science and the lessons we can learn from its darker chapters.
Yeah, for sure.
Thank you for guiding us through this deep dive.
As we conclude, I'd leave you with this thought.
Okay.
If the pursuit of scientific advancement is a journey into the unknown, then the lessons learned from past mistakes are the maps that can help us navigate that journey safely and ethically. It's up to all of us to study those maps carefully and use them to chart a course towards a future where the power of nuclear technology is harnessed responsibly for the benefit of humankind.
A perfect note to end on. Thank you for listening, folks, and until next time, keep exploring, keep questioning, and keep diving deep.